Hi everyone, welcome to Studia Academy Past Paper Walkthrough. In this video, we will be discussing IGCSE Edexcel Chemistry, May 2024, Paper 1C. Let's go through the first question step by step. It gives us a list of substances: bromine, chlorine, diamond, ethene, iodine, lithium, methane, and water. First, part A asks us to match each description with one substance. We can use a substance once, more than once, or not at all. First, for a good conductor of electricity, I chose lithium because it's a metal with delocalized electrons. For an element that is a liquid at room temperature, the correct substance is bromine. The description, a substance that can be used to form a polymer, refers to ethene, as it's an alkene that undergoes addition polymerization. For an element that forms a basic oxide, the answer is lithium again, since metal oxides are basic. And finally, for a substance that has a giant covalent structure, the answer is diamond. For part B, the question is to describe a test for chlorine. The standard chemical test is to use damp blue litmus paper. The positive result is that the paper is bleached white because chlorine reacts with water to form acids that remove the color from the dye. This type of question is very commonly asked in IGCSE Edexcel Chemistry, so it's worth the time to memorize your chemical tests. Next, question 2 asks about the reactivity series of metals, a fundamental concept. Let's break down this first experiment on metal reactivity. We have 4 mystery metals, P, Q, R, and S, that were tested with dilute hydrochloric acid. The results gave us a clear order. Q is the most reactive, followed by S, then R, with P being the least reactive. This is a classic reactivity series investigation. Next, which one could be zinc? Well, zinc sits in the middle of the reactivity series. It's not super reactive like Q, but it's more reactive than metals like copper. Looking at our order, R is in that middle position, making it a perfect candidate for zinc. Next, we need the word equation for aluminium and acid. That's straightforward. Aluminium plus hydrochloric acid yields aluminium chloride and hydrogen gas. Now, metal P. Since P shows no reaction and is at the bottom, it must be a metal below hydrogen in the reactivity series. That means it could be copper, silver, or gold metals that don't react with dilute acids at all. Finally, a safety note. Why shouldn't we react metal Q with the acid in a simple test tube? Because if Q is something like sodium or potassium, the reaction isn't just fizzy, it's violent, explosive, and dangerously unsafe. The hydrogen produced can ignite instantly. Now, part B. Let's apply this idea of reactivity to a dramatic real-world process, the thermite reaction. In this setup, we have a mixture of aluminium powder and iron 3-oxide powder. When ignited by a magnesium fuse, it triggers a spectacular and incredibly exothermic reaction. The chemical equation is Fe2O3 plus 2Al yields 2Fe. Plus Al2O3. So, what does exothermic mean? It simply means the reaction releases heat energy to the surroundings. You can see the molten iron glowing because of that intense energy release. Why does this exothermic reaction work? It's a direct application of the reactivity series. Aluminium is more reactive than iron, so it can displace iron from its oxide. This is a displacement reaction. And this isn't just displacement, it's also a perfect example of a redox reaction. Here's why. Aluminium is oxidized because it gains oxygen to form aluminium oxide. At the same time, iron 3 oxide is reduced because it loses its oxygen. Since both oxidation and reduction are happening together, we classify it as a redox reaction. Both approaches to this question can earn you 2 marks. Next, question 3. Asks about relative atomic mass, isotopes, and electron configuration. Let's look at an atom. How do you find its group? Count the outer shell electrons, so element Z is in group 2. Now, its period? Count the electron shells. So the answer would be 3. Now part 3 wants you to give the formula of the compound that forms when Z reacts with fluorine. How do we do this? To find the formula of its compound with fluorine, use ionic crossover with your valencies. Therefore, that would give you ZF2. Now part B. You need to remember 1 mole of any substance contains the Avogadro constant of particles, which is 6.0 times 10 to the power of 23 atoms, a good value to remember for the future. Because we have 12 electrons in this element, we need to times our Avogadro's constant by 12. Therefore, 1 mark is given for writing 12 times 6.0 times 10 to the power of 23, and for the second mark for writing correctly in standard form, 7.2 times 10 to the power of 24. Next, question part C. We are given a sample of element Z, which contains 3 isotopes, and a table showing the numbers of particles in the nucleus of each isotope and the percentage abundance of each isotope. We need the relative atomic mass, AR, from isotope data. So we will calculate using this formula, mass times percent abundance. For each, sum them, and divide by 100. Our final answer gives us 24.3. Now, part D, looking at the periodic table. The element with a relative atomic mass closest to 24.3 is magnesium. This fits perfectly with our earlier deduction that Z is in group 2, period 3, which is exactly where magnesium is located. So the element Z is magnesium. Question 4 is a great question that contrasts different types of bonding using caffeine and calcium bromide. First, you have to understand the basics for caffeine. Let's do a recap of molecular formulas together. It is the chemical formula of a molecular compound that shows the kinds and numbers of atoms present in a molecule of the compound. Caffeine's molecular formula is C8H10N4O2. So, in one molecule, you just add up the atomic mass. 8 plus 10 plus 4 plus 2. That's 24 atoms in total. To find its relative formula mass, or MR, you do a sum. 8 times 12 for carbon, plus 10 times 1 for hydrogen, plus 4 times 14 for nitrogen, and 2 times 16 for oxygen. That works out to 194. Remember, there are no units for MR. The empirical formula is the simplest whole number ratio of these atoms, which for caffeine is actually the same as its molecular formula. Now, part B, the question then asks about how ethanol can be extracted from a solution of caffeine. The separation method shown is classic simple distillation. Now, the mixture of caffeine dissolved in ethanol is heated. Ethanol has a much lower boiling point. Its vapor rises, enters the condenser, that's apparatus X, where it's cooled by the cold water jacket and condenses back into pure liquid ethanol, which is collected. The next part is arguably the hardest part of this question. Why does calcium bromide have a melting point over 500 degrees higher, even though their MR values are similar? Have a think. Well, it all comes down to bonding. Calcium bromide, CaBr2, is an ionic compound. It forms a giant ionic lattice held together by incredibly strong electrostatic forces of attraction between the positive calcium 2+ ions and negative bromide- ions. Breaking this for melting requires a huge amount of energy. Caffeine, on the other hand, is a simple covalent molecule. Within each caffeine molecule, atoms are held by strong covalent bonds. But between one molecule and the next, there are only relatively weak intermolecular forces. It's these much weaker forces that need to be overcome to melt caffeine, which requires far less energy. This is the perfect example of how the type of structure and bonding gives the molecule its property. For question 5, let's look at 2 key practical techniques, chromatography and flame tests. This question tests if you really understand the why behind chromatography. First, look at the diagram. The key rule is that the initial spots of ink must be placed on the baseline above the level of the solvent in the beaker. Why? 2 reasons. If the spots were submerged, the dyes would simply dissolve and diffuse into the large volume of solvent in the tank, ruining the separation. Placing them above ensures the solvent moves up the paper, picking up and carrying the dyes with it at different rates. Now, look at the final chromatogram. Which 2 pens contain the same dye? The answer is E and H. How do we know? Their colored spots have traveled exactly the same distance from the baseline, meaning they have the same RF value and they are the same color. Both conditions must be true. The next part asks us to explain why the student is wrong. The student thought both F and G contained only one dye. They can only be certain about pen G. Why? Pen G produced a single distinct spot. Pen F, however, might contain a mixture where two dyes have identical RF values and colors, so they overlap completely and appear as one spot. Chromatography can prove a substance is impure, multiple spots, but it can't conclusively prove a substance is pure from a single run with one solvent system. The final part of the question 5 wants us to calculate the RF value. The RF value is a constant for a given dye under specific conditions. The formula is RF equals distance moved by spot divided by distance moved by solvent front. For the dye in G, measure the distance from the baseline to the center of its spot. Then measure the distance from the baseline to the solvent front. That's the level the solvent reached. Next, part B. Before testing a new sample, it's crucial to clean the platinum or nichrome wire by dipping it in hydrochloric acid and then holding it in a hot Bunsen flame so as to remove impurities that interfere with experiment. We repeat this until the wire doesn't add any color to the flame. If we didn't, those contaminants could give a false positive result. We might see the wrong color and misidentify our unknown ion. Next question. Once clean, we dip the wire in our sample, say a white solid suspected to contain lithium ions, and place it back in the flame. If lithium is present, we'll observe a crimson-red flame. Each group 1 ion has a unique color, and crimson red is the signature for lithium. That's why the answer is C. Next, part C. Let's break down a compound you might find in baking powder, potassium aluminium sulfate. First, we have the potassium ion, which you'll recall from group 1, with a charge of K+. Next is the aluminium ion. Aluminium is in group 3 and typically forms an Al, 3+ ion. Finally, the polyatomic sulfate ion has the formula SO4, 2-. Now, this salt is often found as a hydrated salt, meaning water molecules are trapped within its crystal lattice. Our job is to find X, the number of water of crystallization. We're told that 23.7 grams of the hydrated salt produces 12.9 grams of the anhydrous salt after heating. The difference is the mass of water lost. Mass of water equals mass of hydrated salt minus mass of anhydrous salt. Therefore, mass of water is 23.7 grams minus 12.9 grams, which equals 10.8 grams. So 10.8 grams of water was driven off. We do the same for water with an MR of 18. 10.8 divided by 18 gives us 0.6 moles of water. Finally, to find X, we find the molar ratio. We divide the moles of water by the moles of the anhydrous salt. 0.6 divided by 0.05 equals 12. Therefore, X equals 12. The full formula for the hydrated salt is K, Al, SO4 twice, dot, 12, H2O. This process of thermal decomposition to find water of crystallization is a key practical technique. Let's move on to question 7 now. First up, a quick fact check. What's the approximate percentage by volume of nitrogen in the atmosphere? If you said a whopping 78% or 80%, you're spot on. That's option D. It's the most abundant gas in our air. Now, how do these nitrogen atoms stick together? We need to complete a dot and cross diagram for an N2 molecule. Remember, nitrogen is in group 5. Each atom has 5 outer shell electrons. They form a triple covalent bond. That's 3 shared pairs of electrons to achieve a full outer shell. This strong triple bond is why nitrogen gas is so stable and unreactive. Now part C. When fuels burn in car engines, they can produce nitrogen dioxide, or NO2. This gas doesn't just sit there. It reacts with water vapor and oxygen in the air. The product? Nitric acid, HNO3. The balanced equation is 4NO2 plus 2H2O plus O2 yields 4HNO3. Next question. This nitric acid falls as acid rain. One major environmental effect, it corrodes buildings and statues made of limestone or marble. It also lowers the pH of soil and lakes, harming plants and aquatic life. Part D. For this part, look at the charge of both ammonium ions, NH4+, and carbonate ions, CO3-2. Remember the ionic crossover method to deduce the formula? Use it and we will get NH4, 2, CO3. Finally, let's play lab detectives. Say you find an unlabeled bottle that might be an ammonium carbonate solution. How do you confirm it? You need to test for both ammonium ions, NH4+, and carbonate ions, CO32-. The first step is to test for carbonate ions. Add a few drops of a strong acid, like dilute hydrochloric acid. If carbonate ions are present, you'll see effervescence, fizzing, as carbon dioxide gas is produced. To confirm it's carbon dioxide, bubble the gas through lime water. If it's a carbonate, the lime water will turn cloudy or milky. The second test is the test for ammonium ions. For this, we use sodium hydroxide solution. Warm a fresh sample of the solution gently with some NaOH. If ammonium ions are there, they'll release ammonia gas, NH3. You can test for the ammonia by holding damp red litmus paper at the mouth of the tube. The alkaline ammonia gas will turn it blue. Question 8 is all about hydrocarbons, compounds made of just hydrogen and carbon. First up, isomers. What does that mean? Simply put, isomers are different compounds that share the same molecular formula. They have the same number of each type of atom, but their atoms are connected or arranged in completely different ways. Our molecular formula is C4H8. This is an alkene, so it must contain at least one carbon-carbon double bond. The question gives us one isomer, but one ene. Our job is to draw two more isomers. Remember, the double bond can move, or the carbon chain can branch. For isomer 1, we can move the double bond to the middle of the chain. This gives us but 2 ene. For isomer 2, we can also create a branched chain. This one is called methylpropene. Here the main chain is 3 carbons long with a double bond, and there's a methyl group as a branch. Next, reactions. But 1, ene reacts with bromine. The orange bromine water is decolorized and we get a new compound, C4H8Br2. This is the classic test for unsaturation. What type of reaction is this? It's an addition reaction. The carbon-carbon double bond opens up and 2 bromine atoms add directly across it. No other product is formed. This is the key difference from alkanes, which undergo substitution. Finally, let's talk about big molecules, polymers. The alkene C3, H6, is propene. It can undergo addition polymerization to form polypropylene. To draw the repeat unit, you take the monomer, break the double bond, and extend the bonds out into a chain. The repeat unit for polypropylene is CH2, single bond, CH, with a CH 3-side group attached. This structure repeats thousands of times to form the long polymer chain. What happens to this plastic when we're done with it? We need to state an environmental problem for 2 common disposal methods. Method 1, burying in landfill sites. The big problem here is that most polymers like polypropylene are non-biodegradable. They don't break down naturally for hundreds of years, taking up vast amounts of space and causing long-term land pollution. Method 2, burning to release energy. The major environmental issue here is air pollution. Burning plastics can release toxic gases and particulates into the atmosphere. If the combustion is incomplete, it can also produce the highly toxic gas, carbon monoxide. Furthermore, the next question asks about an unknown alkane burning completely. We know the products are 396 grams of carbon dioxide and 180 grams of water. From just this, we need to figure out the balanced equation by finding the coefficients y-x, y, and z. We are told the relative formula masses, or MR, for carbon dioxide it is 44, and for water it is 18. To calculate the mole, we use the mass divided by the MR. For carbon dioxide, the calculation is 396 grams divided by 44 grams per mole, which equals 9 mole. Therefore, Y equals 9. Next, for the water, 180 divided by 18 gives us 10 moles. Therefore, Z equals 10. That's our Z. This tells us we produce 10 moles of H2O. Since each water molecule has 2 hydrogen atoms, this means the alkane must have contained 20 hydrogen atoms. So, our mystery alkane is no name, C9H20. The combustion equation is now C9H20 plus XO2 goes to 9CO2 plus 10H2O. Finally, we balance for oxygen to find X. On the right, we have 9 times 2 plus 10 equals 28 oxygen atoms, so we need 14 O2 molecules on the left. Therefore, x equals 14. Now, part E, the real world isn't perfect. In a petrol engine, there's often a limited supply of oxygen. This leads to incomplete combustion. Take octane C8H18. Instead of forming just CO2 and H2O, it produces a nasty mix. For this specific equation, we balance it to get C8H18 liquid plus 9O, 2 gas goes to 5, CO gas plus 3C solid plus 9H2O gas. Next question, notice the products. Carbon monoxide, CO, a poisonous gas, and carbon, C, which we see as soot or particulates. Now explain one problem for humans from this. The major issue is carbon monoxide poisoning. CO binds irreversibly to hemoglobin in red blood cells much more strongly than oxygen does, forming carboxyhemoglobin. This drastically reduces the blood's oxygen-carrying capacity, leading to dizziness, loss of consciousness, and even death. It's a silent, odorless killer. Question 9 puts us in the lab to study the rate of a reaction, specifically the reaction between marble chips, that's calcium carbonate, and dilute hydrochloric acid. We'll use a clever method and analyze a graph to understand what's happening. Let's look at the setup. We have marble chips and acid in a flask, but instead of collecting the gas, the flask is sitting on a balance, and there's a loose plug of cotton wool in the top. During the reaction, the balance reading decreases. Why is mass lost? This is the key to the method. The reaction produces carbon dioxide gas, CO2. That gas is less dense than air and escapes through the cotton wool. Since the CO2 leaves the flask, the total mass of the flask and its contents goes down. The mass loss directly tells us how much gas has been produced. So what's the cotton wool for? It's a safety and accuracy feature. It allows the carbon dioxide to escape, which is essential for the mass to change, but it also prevents any acid spray from the fizzing reaction from getting out. This is important for safety and to make sure we're only losing gaseous products. It starts steep, curves, and eventually becomes a flat horizontal line. The question says to assume the marble chips are in excess. So what's going on? First, the steep start. At the beginning, the concentration of hydrochloric acid is at its highest. There are loads of acid particles available to collide with the marble chip surfaces. The rate of reaction is fastest here, so we lose mass, produce CO2 quickly, a steep slope. As the reaction proceeds, the acid is being used up. Its concentration decreases. Fewer acid particles mean fewer successful collisions per second. The rate of reaction slows down. The slope of the graph becomes less steep. The graph eventually becomes horizontal. This means no more mass is being lost. The reaction has finished. Why? Because the limiting reactant, in this case the hydrochloric acid, has been completely used up. Even though we have marble chips left, they were in excess, there's no more acid to react with, so the reaction stops. So this experiment gives us a beautiful way to track rate by measuring mass loss. The shape of the graph tells the whole story. A fast start due to high concentration, a slowdown as the acid is used up, and a stop when the limiting reactant runs out. Now, what if the student repeats the experiment using the same volume of hydrochloric acid, but with half the concentration? The new curve would still start at the origin. But because there are fewer acid particles from the beginning, the initial rate is slower, so the curve will be below the original curve throughout. Also, since the volume is the same but concentration is halved, only half the amount of acid is available to react. The total mass loss will therefore be half of the original, so the curve levels off at 0.27 grams, exactly half the original final value of 0.54 grams. And we're on to the final question 9. We need to explain how using smaller marble chips affects the rate of reaction. So if the student repeats the experiment with smaller chips, the rate of reaction would increase. It would be faster. The key reason for this is that by breaking the chips down into smaller pieces, you are increasing the total surface area available for the reaction. According to the collision theory, for a reaction to occur, the reactant particles need to collide with enough energy. Because we now have a larger surface area, the acid particles have more area to target on the marble. This means that there will be more collisions per unit time between the acid and the marble. Since there are more frequent collisions, the successful rate of reaction goes up. And we're on to the final question of the paper. We're going to measure the enthalpy change for a classic reaction, magnesium reacting with dilute nitric acid. This involves careful measurement, a bit of math, and knowing how to get the most accurate results. First, let's complete the equation. Magnesium is a reactive metal. It displaces hydrogen from acids, so magnesium plus nitric acid gives us magnesium nitrate and hydrogen gas. The balanced equation is Mg plus 2, HNO3, yields Mg, NO3 twice plus H2. Now part B, the method. The student records the start temperature, adds the magnesium, and notes the highest temperature. We're given the temperature rise is 16.4 degrees Celsius. Looking at the thermometer, we need to read it to the nearest 0.1 degrees Celsius. The start temperature looks like 30.0 degrees Celsius. The highest temperature would be the start plus the rise. 30.0 plus 16.4 equals 46.4 degrees Celsius. So our table is start, 30.0 degrees Celsius, highest 46.4 degrees Celsius, rise 16.4 degrees Celsius. For part C, it is time for calculations. We need to find the heat energy change, Q. We use the formula. Q equals m times C times delta T. M is mass of solution. We had 40 cubic centimeters of acid, and we assume 1 cubic centimeter equals 1 gram, so M equals 40 grams. C is the specific heat capacity, given as 4.2 joules per gram per degree Celsius. Delta T is the temperature change, 16.4 degrees Celsius. Q equals 40 grams times 4.2 joules per gram per degree Celsius times 16.4 degrees Celsius. Q equals 40 times 4.2 times 16.4. Q equals 2755.2 joules, which is approximately 2800 joules. So Q is approximately 2800 joules. This is the energy released for the amount of magnesium we used. Now for the big one, the enthalpy change, delta H, in kilojoules per mole. We use 0.12 grams of magnesium. The relative atomic mass of Mg is 24. Moles of Mg equals mass divided by relative atomic mass, which is 0.12 grams divided by 24 grams per mole, equaling 0.005 moles. First, find moles of magnesium. 0.12 so divided by 24 equals 0.005 moles. Q for 0.005 moles equals 2800 joules, which is 2.8 kilojoules. Delta H equals energy divided by moles, which is 2.8 kilojoules divided by 0.005 moles, equaling 560 kilojoules per mole. The reaction released 2800 joules, which is 2.8 kilojoules. This was for 0.005 moles. To find delta H per mole, we do 2.8 kilojoules divided by 0.005 moles equals 560 kilojoules per mole. Crucially, we must include the sign. The temperature went UP, meaning the reaction released heat. It's exothermic. So delta H equals minus 560 kilojoules per mole to two significant figures. Finally, why use a polystyrene cup instead of a glass beaker for a more accurate result? This is all about reducing heat loss. Polystyrene is an excellent thermal insulator. In a glass beaker, a significant amount of the heat energy from the reaction is lost to the surroundings by conduction through the glass and by convection to the air. This makes the measured temperature rise smaller than it truly should be. Using a polystyrene cup minimizes this heat loss, so more of the heat energy stays within the reaction mixture. This gives us a larger and more accurate temperature rise, leading to a more accurate and more exothermic calculated value for delta H. Thank you for watching. Education made easy with Studia.